Hello, everyone. My name is Xue Liang. I'm currently the tech lead and engineer in LCG ART team. So in this talk, I will give an update of the Android runtime development in our team in the past year. So here is the agenda. I'll give a quick introduction of current status of the LCG ART team. And I'll go over all our big accomplishment in the past year, including the compiler optimization achievement, the new architecture features that we developed, and the tools and testing improvements that we've done for ART. And hopefully we have some time for Q&A. So here's the status of ART team as of today. Our team has 5 engineers, all from ARM. And in the past few years, actually, our team has been the most active contributors to the ART project. Of course, ART is owned by Google, so the Googleers are the most active contributor and maintainer of the ART project. But if you count the non-Googler contribution, actually in the past 12 months, the LCG ART team has contributed 133 patches and merged in AOSP ART, and this is more than any of the other contributor combined last year. And this year, our focus on our project has been developing compiler optimizations and code size improvement for the 64-bit backend, and try to enable new architecture features in ART. Most of them belong to the v.x instruction set. And we contributed various testing improvements, especially those improvements to help testing those new architectural features. So if you're a now member, and if you're interested in our work and plans, you can visit our LCG 390 initiative card for more details. So let me quickly introduce our work on the compiler optimization direction. So the motivation of this work is that we want to make sure that the ARM backend delivers the best performance for ART project. And we want to make sure that we develop really valuable and useful optimizations for our Lenovo members and upstream projects. Actually, we do not just do compiler optimization randomly. So every once a year, we usually do deep dive performance analysis on current workloads and find out the most valuable optimization area that we can optimize on. Here's a sneak peek of our very recent findings on the ART workloads this year. So we found some strength reduction opportunities for the division operations, some improvement in the array bounds check elimination, and jump threading optimization opportunities. So if you're interested in our performance analysis and the benchmarks analysis, my colleague Evgeny will give a talk later today on the details of this work. So if you're interested, please join his talk. So here are some highlights of the optimizations we've done in the past year. First of all, we optimized the ART stack map format in the ART compiled old file. This gives a very significant code size reduction. For example, this optimization alone saves 5% code size for the system boot.old file. We optimize the ART get charts intrinsic with Neon implementation. And we've tested this optimization on Pixel 3, and we found that this can give up to 80% speed up on long strings operations. We introduced SIMD support in the load store elimination optimization in ART, and we optimized ART's HDIV and HRAM codegen with LSR and ASR instructions. Another major direction we're working on for ART is try to introduce and enable more ARMv.X features. So in the past few years, we've seen that Android phones with ARMv.2 and later features start to appear in the market. I think for our members and partners, it's really important that these newest architectural features is fully exploited in their product. And I think ART is such a unique layer in Android software stack, because once we can introduce and enable those features in ART, thousands and thousands of applications can automatically benefit from these optimizations and can make big performance improvements, because they are all compiled by ART compiler at the end of the day. So let me show a few examples of the optimizations we've done using ARMv.X features. We found that in Android API, there is a half class which does this 16-bit half floating point operations. And actually, all those half floating point operations can be optimized using ARMv.2 FP16 instructions. For example, the half to float API, as shown on the slide. Currently, the original Java implementation, as you can see, is a very complicated algorithm and is a pure software implementation in Java. So even we use ART optimizing compiler, this method can easily compile into 40, 50 instructions. But now, since we have this very nice 3.2 FP16 instruction set, this two float operation can be implemented in just two FP16 instructions, as shown on this slide. So this is done by ART analyzing all the core side of these half methods and use intrinsic optimization to inline the cores by using FP16 instructions. So this is significant performance improvement than coding into the Java implementation. So currently we have 9 half APIs optimized using FP16 instructions in this way. I would like to thank our colleague Usama, who implemented all these optimizations. So if you're interested, you can click on the link and see all the optimizations we've done using FP16 instructions. The next example I want to show is the dot product instructions. So I think nowadays dot product computation pattern is more and more common in many workloads, especially in machine learning workloads. So as you can see on this slide, this is a dot product computation implemented in Java. So we have introduced optimization in ART to help ART to teach ART compiler to recognize this dot product loop pattern and auto-vectorize it and replace the loop kernel with a single s dot and u dot instruction. Again, this will be a very tremendous performance improvement comparing to non-dot product and non auto-vectorized loop implementation. We not just only introduced this optimization in ART, we also introduced a dot product CPU feature detection and the testing of this compiler optimization. So if you're interested, you can click on the link and see the details of this optimization. So let me talk about the most exciting features that we are working on right now. So currently we are trying to introduce the SVE instruction in ART. So we're trying to teach the ART auto-vectorization phase in compiler to recognize Java loops and auto-vectorize it with the SVE instructions. And unfortunately, currently there is no actually Android platforms that actually supports the Java the SVE features yet. So currently we are developing the functionality and the algorithm side in the compiler to get really ready for the future platforms that supports the SVE features. And our development is currently based on VXL Simulator, which I will introduce later. So here is the status of our SVE patches. Our CPU feature detection of SVE features is done. The codegen support in ART of SVE is done. And we have also introduced the predicated vector instruction support in ART. And currently we are working with Google to update the VXL in the AOSP project to introduce the VXL SVE support in the AOSP version of VXL. So currently this work is ongoing upstream. So if you're interested, here's a link. You can click on it and take a look. So let me quickly show you how SVE optimization may look like in ART. Currently we're trying to improve the ART auto-vectorization path to recognize some loop and auto-vectorize it with the SVE instructions. Here is one of my favorite loop example of how ART can optimize a loop with SVE instruction. As you can see that this is a very simple computation. This loop take array and do some perform some operations on the array. Note that there is an if inside this loop, and actually some of the array element gets to updated in the loop, and some of the array element remains untouched. So this is actually quite challenging control flow if you think about how we can auto-vectorize it and using neon instructions. But thanks to the SVE's new predicated execution feature, we can easily auto-vectorize this loop with SVE instructions governed by the predications. There's a example on the right side of the slide. You can see how it is auto-vectorized with SVE predicated instruction. So another highlight of our work is really the ART development and feature testing improvement. So I've been working in ART for several years, but this year I feel that the tools and the development support is much improved with all the tools we've contributed, especially on testing the new architecture feature side. We've done a lot of work there to make sure that ART is ready for testing and for developing new architectural features. So the first work we've done regarding improvement testing is that we improved our current benchmarking script with SimplePerf support. So SimplePerf is currently the standard performance analysis tool on Android platform instead of using the old perf tool. So now this new tool is fully integrated in our benchmarking script, analysis script as well, and also introduced a perf to CFG tool to actually combine the output of SimplePerf profiling data with the ART compiler generated CFG file, so that our compiler engineers can easily browse in tools like C1 Visualizer and see block level or instruction level hotspot in certain function that he's analyzing. I would really like to thank our intern Emma, who developed this very nice feature, and this feature is also accepted in the AOSP as well. For the new architectural feature development and improvement, we've developed improvement to the current ART checker test framework, so that now the checker test supports conditional statement in its test conditional statement. So it's easy for us to test all those optional v8.x features that we introduce in the compiler, like dot product, SV, etc. I would like to thank our engineer Fabio, who upstreamed and developed this nice feature. And last but not least, we start to use more VXL Simulator more in ART project. So VXL Simulator is actually part of the VXL project. It supports emulating all instructions emitted by the VXL assembler. It performs pure software emulation. It is really useful in testing and debugging assembly snippets generated by the ART compiler. And we use the standalone simulator in developing, testing our new architectural features like SV, FP16, etc. And we also developed a patch to integrate the VXL simulator in ART, so that many ART test cases can directly test it on the VXL simulator. And if you're interested, here's a link. You can take a look the patch. However, this patch is not up to date. So if you are a Linaro member, you can contact ART team. We can give you a much up-to-date VXL simulator integration patch that allows you to test the ART tests and new features on simulator. So I believe this is my last slide. So we are a team of very happy and very active ART contributor. So if you're interested on all our work and optimization we've done for ART, you can click on the link and take a look. And our focus this year has been performance improvement, code size improvement, new architectural feature enablement in ART, and development tools and testing improvement. And of course, we'll always like to hear the feedback from our members and partners on what you would like to see that the LCG ART team would do to help improve your product, your platform, etc. And as always, if anyone would like to put new assignees to the LCG ART team, that would be fantastic. Yeah, I think this is my last slide. With that, I would like to say thank you.